Today we are going to be talking with Eric Larson, and we're going to be going over optimization with OptiStruct. To introduce myself, I'm Shannon Earls. I've worked with many of the teams as I head up our competitive sports sponsorship here at Altair. So some of you on the webinar today might recognize my name through the emails that we've had in discussion, and it's nice to meet you again through the webinar. Today our trainer is going to be Eric Larson, and just to give you a little bit of background on Eric, Eric comes to us with over 20 years of industry experience. 10 years he's been with Altair. He's currently our U.S. training manager with extensive experience in both HyperMesh, HyperView, OptiStruct, and Inspire. So we're going to be learning a lot today with Eric over OptiStruct. Just some few housekeeping notes as well. Everyone will be muted during this webinar. We are recording the session, and there will be a link sent out to everyone who has registered after the webinar is complete. And please use your question window to ask questions, and we will answer these through the webinar with Eric when time is available as well. At the end of the webinar, I'm just going to go over briefly how your team can obtain sponsorship from Altair, and also how to get the student version and where you can find some of our training materials on our university website. And again, we'll show you a little bit about the William Adam Award that we do offer at the Brooklyn, Michigan event as well. Without further delay, I would like to turn the tables over to Eric to give you guys the OptiStruct demonstration.
So there we go. Okay, so hopefully you all can hear me. Let me come here and show my screen. There we go. We good? Can you see my screen? Okay, perfect. Okay, just making sure that that I'm broadcasting properly. So what I'm here to talk to you about today, first of all, thank you, Shannon. I appreciate the introduction. I'm here to talk to you about optimization using our OptiStruct product. And the idea of concept and fine-tuning your design. I promise you I'm going to try to keep the slides to an absolute minimum. I have a number of them here that I want to talk about just because I think they kind of show the product well. But a lot of what I'm going to do is going to be demonstration. Now, unfortunately, this hour and a half session is not designed to be a training class. It takes me a fair amount more time to be able to train you how to use OptiStruct. But this webinar is more to provide you with information about what OptiStruct is capable of, what our software is capable of, and what you can do to your designs, to your vehicles, to your projects using OptiStruct. So OptiStruct is a gradient-based approach, or gradient approach design or optimization platform. It uses a gradient approach where it attempts to minimize by evaluating the gradient of the response to make sure that it's continually going down. What OptiStruct does is we pre-process in HyperMesh, we run the optimization in OptiStruct, and then use our suite of post-processing tools, HyperView, HyperGraph, or even HyperView Player to post-process your results. So what this slide is going to show is all of the different optimization types that we can do within OptiStruct. The first of which, and probably the optimization method that is used for, I'd say easily 70 to 80% of all optimizations, is topology optimization. And I will get more into it later, but essentially that animation is kind of showing you what what topology optimization does, it takes a large design space and then whittles away the material to provide you with an optimized part. And a number of these I'll show demonstrations of how they're set up and the concepts behind them, so don't feel that this is the last you're going to see of topology optimization. The next type of optimization that HyperMesh or OptiStruct can handle is what we call free size optimization. Free size optimization is similar to topology. It tells you where material is necessary, but it does so by taking the thickness of every single element in your model and varying it between 0, which would indicate that the element is not necessary, all the way up to the maximum thickness that you specify. So whereas topology will add or will either keep or remove an element, free size does something similar by changing the thickness of a shell element. Topography is a design or an optimization methodology that is used to develop a bead structure on a part. So if you want your part to be stiffer, the best way, of course, to do that is to put beads on there. It's essentially a no-cost addition to the part, and it will stiffen your part. And what topography optimization does is determine the best placement for those beads. The next type of optimization is what we call free shape. Free shape does something similar to what you're looking at there. It takes an already designed part and alters aspects of it, alters the shape of certain features on it. You see that these little cutouts here are going from round to more of an oblong shape. You'll also notice that when it's in the round shape, we see a lot of high stress red in this area. So what's happening is the optimization is optimizing that shape to reduce the stress in the design. Shape optimization, excuse me, is our next form of optimization. Shape optimization is a very powerful tool that can allow you to do some pretty drastic changes to your part. Utilizes the morphing technology within HyperMesh. Morphing technology, as you can kind of see in these images, is the ability to take your mesh, take your part, and alter its shape by morphing, changing the shape of the elements that make up your part. And what OptiStruct can do is take the initial shape of your part, take the final altered shape of your part, and determine what the best shape is between those two. Size optimization, probably primarily used as a gauge optimization. In this case, we've got a ladder frame for a vehicle. And each one of these different pieces in there is a stamped piece, and it has its own material thickness, its own gauge. And what gauge or a size optimization does is tell you what the optimum thickness is for each one of these parts. The topology, free size, and topography are what we call concept level design optimizations. They are design optimizations that are done when you, in a lot of cases, you really don't even know what your part's going to look like. Whereas the free shape, the shape, and the size are what we call fine tuning. So these are kind of a second step in the optimization process. We establish the overall shape of our part using the concept level, and then fine tune it with the fine tuning. And all of these are under the purveyance of OptiStruct. OptiStruct can handle all of these different design optimization techniques. And then shape and size can be handled by another of our optimization tools, HyperStudy. I don't know if we have a webinar on HyperStudy, but if it's something that interests you, it's definitely something we can get somebody in touch with you and talk about. So this is just a slide kind of showing or giving you a definition for each one of the different optimization. I'm not going to repeat these. I've talked about them already. In a lot of ways, the reason I include this is because I love this this optimization that was done on this bridge. This was done many years ago by one of our application engineers, and essentially allowed OptiStruct to design a bridge for them. And what I think is coolest about this particular optimization is this: we just let OptiStruct decide what to do. We gave it a large rectangle of material and said, design a bridge for us. And as you can see, it essentially came up with the exact structure of a suspension bridge. And I think this definitely shows what OptiStruct is truly capable of. More definitions. If you ever want to take a look at the definitions, you can just bring this up in the recording and take a look at them, but I've discussed each one of these. This slide shows a real-world optimization that was done, in this case for the Auto Steel Partnership. In this first step right here, this is the current design of a ladder frame for a vehicle. Most vehicles have a frame that looks very similar to this. And it's a design that really hasn't changed much over the years. Everyone has always designed a ladder frame by putting these two rails here, and then we have your cross members. And as engineers and as designers, oftentimes we kind of get stuck in the design rut. We continue to do things because that's the way that they've always been done. And we really don't intuitively come up with an idea that's going to be drastically different, yet still accomplish the same goal. And that's the advantage that OptiStruct has, is it isn't locked into the old way of doing things. It's looking at things from a purely analytical standpoint. So we give OptiStruct this large block of material saying this is where the frame can be. Design a frame for us. And it comes up with something like this. Very organic looking design, but what can happen then is an engineer takes this shape and uses that as a guideline to design an actual rail. And we get this frame now that is substantially different than the standard ladder frame. But most importantly, we see a 20% reduction in mass, and of course, with the way that the automotive industry is heading and the government requirements on fuel economy, and I'm guessing with your vehicles, if you're in Formula SAE, whether you're doing super mileage or whether you're doing some other type of competition, weight savings is drastically important to you. We've increased the torsional stiffness by 31%, which is definitely important. And from a manufacturing standpoint, then this is perhaps one of the most important things, weld length reduction of 50%. So 50% less weld than there was on this initial design. These are the types of things that OptiStruct can do for you. OptiStruct uses a process where we define what we need to know, what our ultimate goal is, and what we can change. So we use this what we call DRCO approach. You see they're underlined here. The DRCO approach works for each one of our optimization techniques, and we start with design variables. What can we change? And that's going to determine the type of optimization you're going to do. We then establish responses. What characteristics, what things within the analysis are important to me? Weight is important to me. Mass is important to me. Stiffness is important to me. Stress is important to me. Material usage, all these things could potentially be important to me. Then I apply constraints to those responses. So I can say, I don't want this to exceed this natural frequency, or I don't want this stress to exceed this value. And then we set an objective. What is our ultimate goal here? Is our ultimate goal to reduce material usage, to maximize the stiffness of the part, to minimize the mass of the part? We determine what we're looking to do with the optimization. And when we set all of these things up in the preprocessor, OptiStruct can then run the analysis. So here's kind of an example, a theoretical example of how optimization is going to work. This is a simple beam. So I've got a cantilever beam here. It's going to be modeled with 1D beam elements, so with a force of 2,400 newtons applied at the end. And our goal here is to optimize the width and the height of the cross-section to minimize the overall weight of this object. And we need to make sure that the stresses do not exceed the yield stress of the material. And then we also set this further restriction that the height h should not be larger than twice the width b. So it's a statement of our problem. And now we begin to define the information necessary for the optimization. So in this case, we establish our design variables. Our design variables are the things that we can change. And what can we change? Well, we can change the base of the part. such that the base will be somewhere between 20 and 40, I would assume, millimeters. We can change the height of the part so that the height will be somewhere between 30 and 90 millimeters. Then we establish our responses. What aspects of this analysis are important to us? The stress, the shear stress, the overall height of the part, and the mass. So all of these things are pieces of information that we're going to want obtained from each iteration of the analysis. And then using these, we're going to constrain them. We're going to say these are the limits that we want. And constraining is very important. I could say, you know what, I want to take this part and I want to minimize the mass and guarantee that I'm minimizing the stress, or the stress isn't going to go over a certain value. Well, guess what the optimum height and base would be to minimize the mass and guarantee that your stress doesn't go over a certain value? 0. That would be the optimum shape. And of course, we don't want 0. So we have to apply appropriate constraints to make sure that our part stays reasonable. So in this case, we're going to constrain the part to make sure that that our stress does not exceed 160 megapascals, our shear stress does not exceed 60 megapascals, and that the height is less than or equal to 2 times the base. And then we're going to set an objective of weight. We want to minimize the mass as a function of base and height. So what mathematically is going to happen is shown off of this chart right here. We'll call this a mathematical design space. So each one of these lines represents a single value of mass. So you can see here, this is mass 7, this is mass 9, this is mass 11. So a combination of the width and the height result in this line, which is a single mass. So now what we do is we begin to eliminate combinations that exceed one of our restrictions. So that's where our constraints come into play. Otherwise, there's no way to optimize something if you don't say get rid of combinations that exceed a certain value. So in this case, this green line is showing us the stress limitation of 160 megapascals, and anything that falls below this line exceeds that stress value. This next is my shear stress. Everything, we don't need to even pay attention to that because everything that could be eliminated by this is already eliminated by our regular stress line. We put another constraint on here that the height has to be greater than or less than or equal to 2 times the base. So anything above this line is eliminated. And then we set the restrictions of the overall height has to be between 30 and 90. And the overall width has to be between 20 and 40. And you're going to see here that what ends up happening is we get this little green triangle. And any combination that falls within that green triangle is feasible. It obeys all of our requirements. So if I come here and I look, 35 and 60 is a feasible combination. It meets every single one of these requirements. But we're not just looking for a feasible combination. We're looking for the optimum combination. And that is the lowest mass part that falls within our feasible domain. And that's somewhere in the neighborhood of 22.5 and 45. That's how optimization works. Now, this is a mathematical, theoretical example of how optimization works, but this is what's going on behind the scenes. Okay, so it looks like we've got a question.
Yes, somebody has asked.
Yeah, I can. I'll repeat.
What is significance of various optimization procedures in OptiStruct? Example being method of feasible design.
Okay, so if I'm understanding the question right, the different types of optimization techniques that we go through, and I can bring that back to here. So all of these different topology, free size topography, free shape, shape, and size, they all strive to meet the same goal, to optimize our part and determine the best part for us. What differentiates each one of these is what we can change. With topology, what we're changing is whether or not an element is necessary. With free size, what we're changing or establishing is the thickness of any individual element. Topography is the overall height location of a node to determine the bead size. Free shape is another nodal-based optimization that changes the location of a node to determine the shape of a part. Shape is based upon morphing. Size is based upon thickness. So we determine what we can change, to achieve whatever our goal is. We determine what we can change to achieve that goal, and that essentially dictates which design process we're going to be using. Okay, so hopefully that answered the question. I promise you I'm getting close to being done with these slides here, and we'll move straight into demonstration. So I'm going to show you this slide, then I'll do demonstrating. We'll come back to the slides in a little bit. But essentially, just wanted to show you that optimization can be done with any of the different types of analyses that OptiStruct can run. The basic analysis, linear, static, normal modes, buckling, and thermal, and some advanced frequency response, random response. Any analysis that OptiStruct can run as a linear static solver can be used in an optimization. And we also can optimize any of these types of entities, solids, shells, 1D elements, using pressures, forces, moments, and force displacement. So all of these things can be utilized in an optimization. But enough of the slides for right now. Slides are boring. Let's talk about an optimization and what exactly goes into an optimization. So let me bring up a part here. So this is actually a part that's in our basic introduction to optimization class that we teach here. Oops, I just grabbed the wrong thing, so let me import this. And we'll grab this, and basic control arm, and import. Okay, so what I've got here, this is already set up for an optimization, but what I have here is a solid representation of a control arm. This is a basic solid representation of a control arm. We didn't want to go overly complex with overly small elements because that doesn't work well in a class. It takes much longer to analyze. So this was just a general kind of a rudimentary design for a control arm, and we want to optimize it. Now, to understand the concepts of a topology optimization, which is what I'm going to demonstrate here, we need to understand the idea of the design versus the non-design space. Design or non-design space, well, I guess we'll start with design space. Design space is the material that can be removed. So think of it this way. I like to use Michelangelo as an explanation here. So about 550 years ago, Michelangelo made a statement, and he obviously said it far more eloquently than I, but he made a statement that when he looks at a block of material, a block of marble, for instance, so imagine sitting in front of you is a large block of marble. He looks at that block of marble, and he doesn't see a block of marble. I look at it, I see a big block of marble and say, hey, what's that big block of marble doing in here? He looks at a big block of marble, and he doesn't see a block. What he sees is the statue that's inside this block of marble. And then his job as a master sculptor is to simply, I guess simply is probably not the best use of word, the best word, but his job as a sculptor is to remove the material that surrounds the statue that he already sees. And I mean, that's brilliant. Most of everything he did or said was brilliant, but it's brilliant in that if you think about it, if you take any material, if you take any block of marble, inside that block of marble is a statue. And if you simply remove the material, that's not needed, you have a beautiful statue. Well, guess what? It works the same way with car parts or airplane parts or whatever. If I give OptiStruct a chunk of material, it will whittle away the material that's not necessary and reveal only the material that's necessary. And that's what we're doing with the design space. Design spaces need to be big and bulky. Essentially, you want to fill up the region of space that your part could exist. You use all of that area, that volume, and you create a design space, and OptiStruct will tell you what material is necessary. So that's what we're looking at in the red here. The red is the design space, the material that can be taken away. And the kind of yellowish green, these are the non-design spaces. So in the case of this control arm, it's very important that you have some place to mount. We can't allow OptiStruct to get rid of material around where this is mounting in the vehicle. So we establish non-design spaces. And we take a part like this, and we establish constraints on it. Let me come to here. So we put constraints on it. We put forces on it. In this case, we've got 3 different forces, 3 different load types, a cornering load, a braking load, and a pothole load. And once that is all set up, this essentially is ready for an analysis. And from there, we simply add our optimization entities. So let me come here and let me edit the topology desvar. So let me grab this design variable here. So the design variable, as you can see, is all of the elements that are in the design space. So I had mentioned the question was how do you what are the different types of analyses, or how do you determine them? In this case, what I can change is whether an element is there or not, whether an element is used in the design or not. So I establish this as my design variable, and I tell it it's a solid element. I set any parameters. We'll talk more about these later, but I don't see any parameters there. Nothing else. I just simply tell it this is the material that can be used. Then I establish my responses, and I have 2 responses here, volume fraction and WComp. So volume fraction is the fractional value of the overall volume of the part. So it's measuring how much material is there. And then I'm setting a response on what we call a weighted compliance. Compliance is the inverse of stiffness. So the compliance of a part is how much it can bend. We optimize things for stiffness by optimizing them for compliance, because to optimize compliance requires the optimization code to minimize the compliance, thus maximizing the stiffness. And from a mathematical standpoint, minimizing in an optimization is better than maximizing. So by minimizing the compliance, we maximize the stiffness. So we're essentially measuring how compliant this material is, or how this part is, and how much material is being removed. And then we set any constraints. We have an optimization constraint here, so let's take a look at that. Edit the constraint. Optimization, edit constraints. So we have set a limit on the volume fraction. So we want this to have no more than 30% of the material remaining. So we've essentially told this, get rid of 70% of the material and minimize the compliance. So make this part, in standard English, make this part as stiff as possible by getting rid of 70% of the material. Or I guess a better way to say it is get rid of 70% of the material, and whatever the material that's left, make sure it's in a location to make the part as stiff as possible. So before I go to the results of this, make sure to see if there's any questions about what's going on.
We had one question. It was, how do you choose between different methods and/or criteria? For example, MFD or the other ones?
MFD. Different criteria. I need a clarification on what they're asking. Sorry, I apologize. Whoever asked the question, if you could just clarify what you're looking to choose. Could you read it to me one more time?
How do you choose between different methods? In parentheses, it says criteria, i.e., MFD or the other ones. Method of feasible design.
Okay. So yeah, I assume hopefully they're talking about the different optimizations that we can do. So let me bring those up again. So again, the way that you determine, the way that you choose between these is what you can change. So if we're looking to determine the overall shape of the part, we may choose topology or possibly free size. But if all we can change is the thickness of the material that we're using, then we would go size. So it all boils down to what about your part can be changed, and that determines the method of optimization that you use. So hopefully that answered the question. Okay, so while we're doing that, let me just bring up the results of this optimization here. So let me come to here. Excuse me. So this should look awfully familiar. This is the part that we saw in HyperMesh. And what I can do now is I can come to here and I can contour my part with element densities. So what are element densities? Let me come back to here now, and let me come to this slide right here to kind of show you what's going on with, thought I had a slide showing it. Maybe I don't. That's fine if I don't. Okay, so what's happening is each one of these elements will be assigned a density. And we need to think of it not in terms of material density. We need to think of it more of a density of importance. How important is that element? And what actually is happening is it's taking a number between 0 and 1. So a value between 0 and 1. And it is taking the Young's modulus of the material for each one of these elements, and it is multiplying it by a value between 0 and 1. And we know that the Young's modulus is essentially the strength of the element, or the strength of the material. So if I multiply that Young's modulus by 1, I'm saying that element is absolutely necessary, and it has to give everything that it can give. If I multiply the Young's modulus by 0, or at least a number incredibly close to 0, 0 just mathematically, technically doesn't work out, I'm essentially saying that element has no structural integrity whatsoever and is not contributing anything to the analysis. So it will take and it will apply a density value to each one of these elements to determine how important it is to the analysis. And now I can contour those. So anything that's red is vitally necessary, and anything that's blue is completely not necessary. And in the first iteration, iteration 0, where we start, these three things are vitally necessary. Why are they vitally necessary? Because I established them as non-design space, telling OptiStruct you can't touch it. And it views everything else as entirely unnecessary. And then what happens is it goes through all of the iterations, all the way to iteration 35, where I can see now what's necessary in my part. And I can even animate that, and you can see how it progresses. Now, it's kind of difficult to see what's going on inside the part. So what I can do, and actually I think this is possibly open up the wrong, yeah, I did. I did not open up the one that, there we go. This is, I know it looks the same, but there's a slight difference. So let me contour this again, element densities. Perfect, okay, so now I can animate this and see effectively how it's going through each iteration and determining which elements are necessary and which aren't. Again, all I'm seeing is the very surface of this. So what I can actually do, and let me average this so it looks, the colors look a little nicer. Then I can come to this ISO value here, use the contour settings, click apply, and let me set this for 0.3, and now I can see how OptiStruct is dealing with this part. It essentially starts out, and let's step through the steps here. So it starts out, it gets rid of a chunk of material, and then begins to manipulate things and build material in some areas and remove material in others, as it determines what material is necessary to make this part as stiff as possible. And we end up with a part that looks like this. We have this little hanging path here, so I can adjust the densities to maybe connect it, or that may be where we're looking at. So this is kind of the idea of the part that we're looking at. And that's how topology optimization works. It determines what elements are necessary, what elements aren't necessary. It carves away at the elements that we don't need. Think of it almost as a load path analysis. And you end up with a part design that you possibly would never be able to think of, because it's analytically determining which elements are necessary and which aren't. But of course, you look at this and you think, well, unless I'm using a 3D printer, this part can't be manufactured. It has cavities in it, and using no traditional manufacturing technique, stamping or casting, could this thing be made. So what we can do is add what we call manufacturing constraints to it. So manufacturing constraints are an indication of draw direction, either single or split. And what that does is, we'll look at it in this slide here, without any manufacturing restrictions, we end up with hollows on the inside of this part, which would be the optimized design. But the single best, most incredibly optimized design is completely useless to you unless you can actually make the part. And so when we add manufacturing constraints to it, in this case a draw direction, we end up with a slightly different design that perhaps isn't as perfectly optimized as this, but is optimized and manufacturable. So if I take this same part and I add what we call a draw direction constraint to it, I can come to here now. So we'll open that up. It looks exactly the same. But what has happened now, and let me open up this in HyperMesh. Again, looks exactly the same, but if I come here and, did I open it? I didn't, I don't think it opened up. Cancel, that's why. File, new. I have to import it again. File, import, solver deck. Come to here, there we go. That's better. So what has happened now is if I come back to my topology design variable, it has added, or what has been added to it is a direction, a draw direction from that node to that node, indicating that whatever my part ends up looking like, it has to be able to be manufactured as if it were drawn or cast in this direction. And what I end up with then is a drastically different shaped part. And then we put the ISO value on here. So you can see that this part could be manufactured in a casting process because we have a direction of draw in this direction. So OptiStruct can not only optimize and help you design the ideal part, it can do so in a way that can be manufactured. Now, I spent most of the time on topology because that is the optimization technique that's most widely used, but let's take a look at some of the other ones as well. 2 questions? Okay, good time to stop. I got 2 questions here. Okay.
The first one is, why minimizing the objective function is better than maximizing?
It's mathematically more stable that way. I don't know the mathematics behind it, but my gut is telling me that when you minimize something, there's a ground floor. You've got 0 essentially is the minimum. So when you minimize, you have kind of a goal that you can that mathematically can be set. You can minimize down to a certain degree, but you can maximize to infinity. Again, I'm not a mathematician, so I don't know the values behind it. I just kind of a gut feeling as to why. But in general, from an optimization standpoint, it tends to work better minimizing than maximizing.
Great. And then the second question was, point 3, is it the density that is not to be retained?
Point 3, yeah. So, well, point 3 is the density of what is to be retained. So, point 3 on your volume fraction indicates that you, and let me come back to that here, just so we know, so I can talk to it. If I come here to optimization, edit, constraints, and I grab that, what happened here? Oh, because I've got the wrong one up. Hold on. File new, and let me import that first solver back in again. And optimization, edit, constraints. So when I come here to my volfrac, this 0.3 of an upper bound is saying that the volume fraction is the fraction of material remaining. So a 0.3 volfrac would indicate that 0.3 of the material, or 30% of the material, is remaining. And when I set an upper bound of that constraint to that, it's basically saying I can only have a maximum of 0.3 of the material remaining. So hopefully that explains it. And if we look here, I can actually also within HyperView, file, open, session, if I come to here to this design history, I can actually get some charts that track my objective function. So let's come to here. So maximum constraint, this is, which one is this? I want to do, oh, why is it not showing me? I didn't plot it. That's a constraint violation, but I want to see design fraction. Okay, it's not showing me a chart for that. That's kind of interesting. Objective function, but not. Huh. Well, I kind of was hoping it was going to show me what the volume fraction was, but for whatever reason, it didn't create a chart for that. What typically it should show me is how that is going away, but apparently it's not showing me a chart for that. But essentially, I'm telling it, remove material, and at the end of the day, you better not have more than 30% of the material that was there to begin with by volume.
And that graph was in HyperView, correct?
Yeah. It's well, this actually technically is in HyperGraph. Yes, yeah. So this framework is what we call our HyperWorks desktop framework, is our post-processing environment. In there we have HyperView and HyperGraph. They can be side by side. I mean, that's a whole nother class to get into. But in HyperWorks Desktop, I could have HyperView here and a graph of that chart right here. So it's in the HyperWorks Desktop. The client for the graphing is HyperGraph. Okay, so the next type of optimization is topography optimization. Topography optimization deals with creating beads. In this case, the design variable now becomes the location of the node vertically, or normal to the material. So if you think about a flat sheet of material, the only thing that separates a perfectly flat sheet of material from material with a bead or a plate with a bead in it is the nodal location. So each one of these represents a node, and each one of these represents a design variable from 0 up to the maximum node height, and that's how beads are created. So we end up with a plate, or we have a plate, we generate the design variable, which is the location of the nodes. It comes up with this part that looks like a topographical view of the Rocky Mountains, and we end up with a part that looks like that. So interestingly enough, in this case, this is a real-world example. We take a thin-walled tank with a fluid, we want to make it as stiff as possible. And in this case, we're going to establish some symmetries. So we talked about manufacturing constraints where we can specify how we're going to manufacture it and allow the optimization to provide us a part that can be manufactured. We can also specify design constraints. So I want to make sure that this part is symmetrical about these 3 planes. And this is the contour that this is the design that we end up with. This is the bead structure that optimization or the OptiStruct comes up with. This is a bead structure that I never in a million years would be able to develop myself. And that's the key to using OptiStruct. Because what do we typically come up with? We come up with bead structures that look like this. And if we get a deflection, this PowerPoint is wrong. Nope, I'm sorry. No, it's right. Yeah, my mistake. We come up with a bead structure like this. We look at the deflection. We say that's too much, so we add more beads to it. And actually what happens is, in this case, it deflects even more. We come up with shapes and designs that often are orthogonal, that are based on things that we've learned in the past. We would never come up with this shape on its own, and what we would come up with would be worse than what OptiStruct can come up with. So some other examples of bead structures in comparison to what OptiStruct developed. In each one of these cases, the deflection and the stress are reduced by the OptiStruct design. Free size optimization, again, is an optimization based on altering the thickness of any individual element. And we end up with kind of truss-like designs. With topology, with free size, we end up with a shear plate type design. And you can see that we get similar results between the two, just 2 different styles of optimization. The one thing that is most interesting about the free size optimization is it lends itself very well to the optimization of composites. Because what can happen is we can establish a base thickness for each orientation of composite, and since OptiStruct alters thicknesses, it will alter the thickness of each one of those different orientations and end up with what we call superplies. So in this case, the ply angle of 0 has this, it's required to have this amount of thickness. 45 and negative 45 this amount, and 90 this amount. Now obviously you can't create a ply that's at that thickness, but what we can do is we can slice those plies, knowing what the ply thickness is. If I know that my ply thickness is 1 millimeter, I'm sorry, Yeah, my overall ply thickness is millimeter, but my sheet is 1/10 of a millimeter thick. I know I need 10 sheets of that ply. So free size optimization works quite well in optimizing composites. So any questions about, any questions about this?
We had a question, yes. Somebody's asking that in the slides it mentions something about importing decks, i.e. a Nastran format, into HyperWorks for optimization. Would it be possible to elaborate on how to do this?
Absolutely. Yeah, so HyperMesh is a universal preprocessor. We support, kind of out of the box, all of the popular solver decks that are out there, solvers that are out there. If you come to this user profile, you'll see a list of all of the different solvers we support right out of the box. So if I wanted to import a Nastran deck, I would come here and I would select, let me start with a blank screen. So if I want to import a Nastran deck, I would establish my profile as Nastran. And this screen with this user profile pops up every time you run HyperMesh. I just already have it running, so I have to come to this icon to change it. So I'm in Nastran, and now I just simply come here and say File, Import Solver Deck. And you see it's looking for BDF or .NAS, the standard Nastran formats. If I had an Abacus deck, I'd select Abacus. And when I go to search for a deck, now it's looking for an IMP file. And then I select that, just like I did with OptiStruct. So when I did an OptiStruct file, I searched for the OptiStruct file, clicked Open, clicked Import. Exactly what I did there with OptiStruct is the exact same thing that you do with any of the solver decks that are out there.
And also another question is, what is the difference between free shape and shape optimization?
Okay, let me show you here. So free shape, probably best to show you the results. So File, New Session. And let me open a session for shape optimization. Okay, so in this case, and let me also open File, New. Let me bring in the model for this shape optimization. Okay, so all of these little gray arrows that you're seeing here are the morphing that have been set up, and they have been saved. And what I can do is, let me come here to morph, and I'll apply a shape. So if I apply a shape, watch what happens. You see how my formerly round hole is now flat on the top and the bottom. And if I apply another shape, it will go to, you know what, let me undo. I need to apply these one at a time, or it's going to get a little awkward. So this shape flattened it out on the sides. This shape made it a perfect square. And this shape made it a very thin rectangle. So what has happened is someone has come along, and inside the HyperMesh software has developed these morphs that has reshaped that tube. And using all of these, setting up an optimization. So let me shape as var. So it has someone has taken each one of these shapes and has set an initial bound and a lower bound, and has said somewhere between the initial shape and the final shape, with all of those shapes combined, is my optimum shape for my part. And what ends up happening is, as we run through the iterations, let me slow this down. See what's happening to this tube? And you can see aspects of all the different shapes that we looked at coming to play here. it's flattening out, it's elongating, and ultimately what's happening is OptiStruct is determining that that is the optimum shape for this part based upon the morphings that were created within HyperMesh. So to do a shape optimization, you have to morph your part first in HyperMesh, and then the optimization will occur between the initial shape and the final shape. So that's shape optimization. Now in free shape optimization, you don't have to set up morphing first. So let me open up the free shape optimization. Oh, there it is, free shape. Okay, so now what's happened is, and I can probably just show it to you here in HyperView, but they have set up an optimization of this compressor bracket. So there is a concentrated mass hanging off of these 1D elements right there. It's a compressor of some sort. And I can't do it. There is a high stress that's occurring in this region here. So we know that there has to be a cutout for this compressor. And we know that we could probably tweak the shape of this curve here that would optimize the part so that we would get rid of the localized high stress. But we don't know in advance what shapes we want to study. And with shape optimization, you kind of have to have an idea in advance what your initial shape and what your final shape would be, because you have to set up that morphing. But with free shape, all I have to say is all of the nodes that are on this curve right here are part of the free shape analysis, and they will move out, in, or both, depending upon what I specify, to reform the shape of this curvature here. Now these points that you're seeing here are a contact location. So what is happening is when this was set up, these were established as this is as far as you can go. So if the shape hits these nodes right here, it will stop and not go any further. So effectively we know that our compressor lies within there, and we wouldn't end up with a bracket that touches the compressor. And now if I take a look at it, you'll see how that shape changes and how it ultimately comes into contact with that but doesn't go any further. Now, I would not have known that this area right here needs to bulge in, whereas this area over here doesn't necessarily. So morphing would have been near impossible for me to do. So the shape optimization wouldn't work well for me, whereas the free shape optimization, where I simply say these nodes on this face can move in or out and not pass this, that's what free shape does for me. So hopefully that explained that well. And just to show you, I've got an example of a free shape optimization here, and this is pretty much the end of my slide. So in this case, we've got a beam here, yet another cantilever. Everyone loves a good cantilever beam. We want to minimize the compliance, and what do we do when we minimize the compliance? We maximize the stiffness. And we want to set a constraint that the volume of this beam has to be less than 4,000 units, cubic units. So with the free shape, we have no idea what this beam should look like. So a free shape design was selected, and all of the nodes that are on this face and on this face were determined to be part of the free shape design variable. And then it was just established that the nodes on the top and the bottom can only move in the XZ plane, and it just guarantees that you end up with a nice flat top or bottom so it doesn't bend or curve. And this is our initial shape. The compliance was 4.1 and the volume was 6,480, which if you remember the requirement was 4,000. So we're starting out of compliance. And this is the end. This ends up being the final shape. So these go in drastically. This ends up just being a thin rectangle. We reduce our compliance down to 3.368, an overall reduction of about 18%, and we went from a 62% constraint violation to exactly where we wanted to be. And this is an animation to show you the iterations that it goes through. That's another example of a shape optimization. And something that would be near impossible to do with true shape optimization because we don't know in advance what our shape would look like to create the morphs to allow this to happen. So I guess let me summarize here by indicating that setting up an optimization in HyperMesh to run an OptiStruct is very easy. We just establish these things right here, the DRCO. We determine our design variable. What can we change? Can we change whether an element is there or not? Can we change the thickness of an element? Can we change the location of a node? That, once you determine your design variable, will determine which type of optimization you're going to run. Then you establish your responses. What are the pieces of information that are important to us from the analysis? Volume, stress, displacement. And the reason we pull those responses and the reason why they're important is because all but one of them will set a constraint. We'll say you can't go beyond this. And the constraints just basically create a bound for our optimization. Allow us to limit it to reasonable or acceptable values. And then the last response, the only one that wasn't constrained, as we said, is an objective. Typically to minimize something, minimize stress, minimize compliance, minimize volume, minimize mass. And that's how we set up for optimization. Again, I apologize. If I had 2 days, I'd love to teach you all the intricacies of optimization and show you how to do it. I've got a little over an hour here, so all I can do is kind of whet your appetite and show you what's out there. We have tremendous resources on the web to show you these different techniques and how to set them up in HyperMesh. When I get done here, Shannon's going to tell you all about how you can get your hands on a student edition of our software to start working on this. But optimization will help you out immensely. It will make your vehicles lighter. It will make them stronger. It will make them better. And I promise you, your competition's already using this. So make sure you take a look at this and start using these optimization techniques to come up with better designs. I know that we've got a good 20 minutes left here on the official time clock. If anyone else has any other questions, I'd be happy to address any of them. And then we'll wrap things up once we get done with any questions.
Perfect. We have one. How can I use optimization to generate lattice structures?
Okay, so lattice structure, I can't answer that directly right now. Lattice structure was actually just added into OptiStruct within the past few months. So for those of you not familiar, lattice structure it goes along with the additive manufacturing or 3D printing, depending upon which way you want to talk about it. When we 3D print things, we typically need to create some sort of structure inside of it to give it some sort of structural support. Think of it as a grid work or a framework on the inside of an object. Lattice structure was actually introduced into OptiStruct within the past 6 months, I think. Unfortunately, I have absolutely no experience with it. I have not done anything with lattice structure. So all I can tell you is it can be done. I believe what happens is OptiStruct generates a series of 1D elements on the inside of the part to create the lattice, and then all of this can be exported out to a 3D printer and an additive manufacturing machine. I'm sure we have tons of literature on it since it's a brand new thing. So take a look at that. I wish I could answer you further other than to say that it can be done with OptiStruct, but at the moment I don't know enough about it to even venture to show you how to do it.
Fair enough. Do we have any more questions out there? Another one is, if I have not defined my problem properly, what will HyperWorks indicate?
Excellent question. Very good question. There's a couple of different ways. First of all, it could just outright fail and say, "There's not. This has not been defined properly. Something's missing." But what also can happen is if you are missing, if you've underdefined, say for instance you've underconstrained your part. A prime example, and this is actually a real world example. Had a new application engineer contact me a few years back because it was very new. He hadn't had a lot of experience with optimization, and he was running into a situation with one of his customers where they were optimizing, running an optimization, and effectively what OptiStruct was doing was getting rid of all of the material. And I laughed and chuckled, a nice, friendly laugh. I wasn't laughing at him, just amused with the results. But what had happened was he had set up the design, the optimization properly. It had all of the pieces that were necessary. But because when you're looking to minimize the mass or the weight of something and get rid of stress, the best way to do it is just to get rid of all the material. OptiStruct was taking that opportunity to do that, and there's your optimized design. So what ended up happening is it was an under-constrained model. It was too free to go to where it wanted. We didn't provide enough, or they didn't provide enough limitations on it to come up with an optimum design. So we put a constraint on the mass to make sure that it didn't get rid of too much, and then it worked perfectly fine. So what the short answer is there are times where if you do not define enough in the output file, it will complain and it will say, here's the problem. But in all too many cases, you've defined enough for an optimization to happen, but under-constrained or potentially over-constrained the model, and it will come up with a design that's strange or possibly report back that there are no feasible designs. It can't come up with a design based upon the input that you've given it, and in which case you typically have to kind of loosen your constraints a little bit. So sometimes it will error out and tell you. Other times you'll know as soon as you take a look at your design and say, whoa, what's going on here?
That's all that we have in the question queue as of this time. I can go and show where we can receive the student edition online.
Okay.
Unless Eric,
no. Okay. No, so that's pretty much it. I appreciate your time. Hopefully you've gotten something out of this. Shannon's going to show you a bunch of information about how to get the student edition, and hopefully also the university website. Make sure you make use of those. There's a ton of information on there, and some great ways to get information. I appreciate your time. Hopefully, look forward to working with some of you guys in the future. And again, thank you for your time, and hopefully you got something out of this. And Brianne, if you're still there, if you could pass the reins back to Shannon, I would appreciate it.
You did get one. We did get one more question, and I will refer back to Eric for that as soon as I show you just a quick excerpt as to where you guys can find everything that you need. Just to show you, this is our Altair University website. You can filter the post by country. I just have it set at United States right now. And real quick, if you look up at the top navigation, you're going to see software. Right here is where you can go to get the free student edition. That's what you guys will be able to use, obviously at no cost. What we prefer to have the teams do is to go under our competition part and go where it says sponsorship form, because we would obviously in the end we would like to sponsor the full team. So with the sponsorship application, it's just very simple. It's just name, college, team name, website, etc. And then in turn we fully support the team, what I mean by that is you get up to 4 licenses for the team to use. The full suite of HyperWorks is available for you as well. There's no limitation on that. And like Eric said, it will include the full suite. So you'll have HyperMesh, Hyperview, Hypergraph, OptiStruct, Inspire, some of our new manufacturing, Click to Cast. You'll have that available. And everything that you do see on our website is offered in that. We also offer support and training for the team and just constant interaction as well. So that is one way which we hope that the teams will go about to get this license if you're not already sponsored by Altair. And to those that are, thank you very much. And we are looking forward to seeing everybody as well. We're going to be at 3 events this year. We're going to be at Michigan Tech for the Clean Snowmobile. We're also going to be at MIS. And then we're going to be at the Baja event in Rochester as well. And one last thing before we get to this last question that I see, I would really like to encourage everyone to please like and follow us on both Facebook, Twitter, any of our social media aspects under Altair University so that you can see and keep up to date with everything that we have going on. We're going to be running some fabulous drawings for the teams to win prizes. We just have a lot of fun and clever things coming up in these next few months. So if you could just go on there as a team and like and follow so that we can also in turn follow you guys and keep up to date with everything that's going on with the teams that we're involved with as well. And then Eric, the question that we had was, is it possible to use a damping optimization in order to improve the MVH characteristic or reduce the vibration transmission of a component?
Wow. Possibly. I don't know. That's beyond what I've done. I've never done MVH analysis. Definitely something worth posting into our university website and see what comes of it there.
Perfect. Yep.
Yes,
and as Eric was saying about that, what I would suggest for the person or anyone that has a question, please use our support forum. You just go right under here. It's the first thing that you see, the support forum. And you can find out, people ask questions. There's tons of answers posted in here. So please feel free to use this. We have our experts that answer the questions for you on a daily basis on this. And if you don't hear from anybody within a day, they'll be right on it as well, like I'm saying. And you can talk with other students, too, to see how they have figured out the problems when they respond to your posts as well, too. So I highly recommend any questions, please go to the support forum for that and post and answer if you're able to help with a fellow colleague's question as well. Oh, was I muted this whole time?
No, I heard you.
One last thing, do we have any more questions? If not, I would just like, again, to say thank you to everybody. Again, you will be receiving this recording in your email shortly, and keep an eye out for our next series. I believe we have one on Tuesday where we're going to be talking about the virtual wind tunnel and how that can help you with your aerodynamic needs as well. And with that, have a great day, everybody.